Hello everyone, I welcome all of you to another lecture of engineering materials. So far now we have studied iron carbon phase diagrams and the different allotrophies of iron. Now today we will be learning about phase and the mechanism of phase transformation. Then we will go to the time temperature transformation diagram for iron carbon system. Now, first of all, what is phase transformation? That is what is important to learn. Now, formation of a new phase in a pre-existing phase is called a phase transformation. Suppose say you've got a glass of water, which is in liquid state obviously. Now, if we want to solidify the liquid or water and turn it into ice, then we would say that phase transformation has taken place. What sort of phase transformation? The liquid has converted into solid. Well, the liquid was the pre-existing phase, and during this phase transformation, a new phase, that is a solid, has been formed. So this is what is phase transformation. Now, the phase transformation process consists of generally two parts. One is nucleation and the second part is growth. Now, what is nucleation? Now, see, as I have told you, the pre-existing phase was liquid. Now, to initiate phase transformation, a small solid phase will be generated, and that is what is called the nucleation. This process phase or a new phase is called nucleation, and this phase is called nucleus. After that, this phase will continuously grow in size, and that part is called the growth. That is the growth of the nucleus. So, first phase transformation generally takes place by nucleation, that is formation of new phases, and then growth of that particular nuclei. Now, nucleation can be of two types, homogeneous and heterogeneous. Now, what is homogeneous nucleation? Homogeneous nucleation is a type of nucleation where the nucleation takes place without the help of surfaces or any defects. But in heterogeneous nucleation, we can see that the nucleation takes place by the help of some surfaces or defects. In general, whatever phase transformation takes place in this world environment, they are generally heterogeneous in nature, but homogeneous phase transformation can be performed in laboratory using certain conditions. Now see, suppose you have got a glass of water. Now if you want to transform its phase into solid, then definitely in case of homogeneous nucleation, you will see that the nuclei will form within the liquid, away from the walls of the container. This is what is homogeneous nucleation, unaided by the surfaces. Surface won't be helping in nucleation. But in actual case, what happens is that the nucleation takes place by the side of the wall. For example, when you are boiling a bucket of water, you will see that bubbles arise, and those bubbles are generally formed along the container walls because the phase transformation takes place along the wall, because the nucleation takes place along the wall. In the same case, if you take a glass of ice, you may say, take out a glass of ice and keep it in a room, then you will see that the ice adjacent to the sides of the walls of the glass will turn into liquid first, and then the middle part will then transform into liquid. So we can see that in general sense, we can see that heterogeneous nucleation takes place. Now, the overall transformation rate, this rate of transformation, it completely depends upon nucleation rate and the growth rate. Nucleation rate is the number of nucleus that can be formed per unit volume per unit time, and the growth rate is in rate of increase of size of the nucleus per unit time. and overall transformation is the fraction of the form of the phase that has transformed per second. Now we will look into some graphs and we will try to explain them why something like this happens. Now we will look at the S curve. What is the S curve? Well, S curve is such a curve where time is given in the x-axis and fraction of the phase that has transformed is given in y-axis. That is, if 100% transformation is taken place, then you may say that suppose say we are considering water that is being transformed into ice. So if 100%, that means the whole water has been transformed into ice, and 0% means no water has been transformed into ice. So with respect to time, how does that transformation takes place? Now we can see that it generally takes place like an S, and so it's called the S curve. Now why does this S curve take place? Now see, we must see the mechanism of phase transformation first. Suppose say we take a glass of water, here the water. Now what happens is, when we gradually cool it, first of all formation of nucleus will be there. Next, what will happen? This nuclei will enlarge, that is, growth of this nuclei takes place, and as well as new nuclei will be formed. Now during the starting phase there are very less number of nucleus and the growth is also less, so the transformation rate is less. But as soon as the transformation keeps on going, we will see that the growth of the nucleus continues and new nucleus are continuously formed. Suppose say here another nucleus has been formed, here another nucleus has been formed. Again the growth will be increased of all the nucleus and new nucleus will be formed. Growth increased. So this part shows the middle section where the rate of transformation is rapid. Other nucleuses will be formed. Again this growth will be the growth of the grains nucleus will be increased. Now see, at this time you will see that the boundaries of two nucleuses which have grown are intersecting each other or are in contact with each other. As a result, what happens is that they cannot grow on that side. So as a result, the growth decreases to some extent, and on the other hand, there is far less liquid in volume where new nucleus can be formed. So new nucleation also does not take place, and as a result, during the finishing phase, when the transformation is almost complete, we see that the rate of transformation again decreases. So during the start of the transformation, the rate of transformation is low because of the less number of nuclei, and at the end of the transformation there is low rate of transformation because of two things. No nucleus is generally formed due to less volume, and secondly, as the grain boundaries touch each other, so the grains cannot enlarge, and as a result the rate of transformation decreases. The next thing is that how does this nucleation rate, growth rate and transformation rate depend upon temperature? Now see, the red line gives the growth rate, the black line gives the nucleation rate, and the blue line gives the transformation rate, overall transformation rate. Now this overall transformation rate depends on G and I, that is growth rate and nucleation rate. It is seen that the nucleation rate is maximum at a lower temperature than the temperature where the maximum growth rate takes place, and the overall thing can be seen as the transformation rate, which is slightly higher than both of these, and the temperature is in middle of these two temperatures. Now we will see the application of this diagram in the time temperature transformation diagram, which we'll be drawing next. Now the time temperature transformation diagram, what does this diagram generally display to us? Now time temperature transformation diagram, or simply called as TTT diagram, or it is often called S curve or C curve. This diagram generally displays the effect of time and temperature on the microstructural changes of a particular composition of steel. Now, for an example, this is the TTT diagram, or time temperature transformation diagram, of 0.8% carbon containing steel, where the austenite has been transformed into certain different iron forms. Now before that, we must know how this diagram is drawn, how we can get this diagram. Now we all know about the S curve that we have studied a bit before. Now at certain temperatures, it can be seen that the time taken for transformation is higher and lower. Sometimes the transformation starts at a certain time and ends at a certain time. For example, at 550 degrees centigrade for 0.8% carbon containing austenite, we can say that the transformation starts very early but ends and also ends at this point. It's also earlier than the transformation that occurs at 200 degrees centigrade. So for a particular type of steel, at certain temperatures, how much time is taken, where the transformation starts and where it ends, this is given by this diagram. There are 4 temperatures that has been taken. One is 550 degrees centigrade, another is 400 degrees centigrade, another is 650 degrees centigrade, another is 200 degrees centigrade. Now if we plot those ends, starting times and end times, in a graph where the x is given by logarithmic value of time and the y gives the temperature. For example, at 550 degree centigrade, it starts at here, this point, and ends at here, this point. At 400 degrees centigrade, say here, it starts at this point and it ends at this point. At 650 degrees centigrade, so here, say, it starts over here and it ends over here. And at 200 degrees centigrade, it starts over here and it ends over here. Now if we draw a continuous curve through the starting points and through the ending points, we'll get a diagram like this, where the black line gives the starting point of transformation and the red line gives the end of transformation. Now this is the TTT diagram for 0.8% carbon containing steel. Now as we know that above 723 degrees centigrade, that is austenite, so there will be austenite, and this is the starting line of transformation, this is the of transformation, this is called the nose. So this is how the TTT diagram is generally drawn. Now see, we must understand what sort of things can we get from it, can we obtain from this type of diagrams, what are the informations that we can get from here. So on a simplified version, it can be seen that this is the TTT diagram, where x-axis, along x-axis logarithmic value of time is given, and along the y-axis the temperature is given. The nose is situated at 550 degrees centigrade, and above 723 degrees centigrade, it's austenite. Now within this range, perlite is generally seen. Within 550 degrees centigrade to 300 degrees centigrade, benite formation takes place, and below 300 degrees centigrade, martensite formation takes place. I guess everyone have heard about martensite, bainite, perlite in the previous video, where I have given the different forms of iron that we are going to study. Now this the rate of cooling, suppose see we are considering about austenite that is stable above 723 degrees centigrade. Above 723 degrees centigrade we are going to get only austenite for 0.8% carbon containing steel. If we look at the iron carbon phase diagram, we can easily see that above 723 degrees centigrade there is only one phase present for 0.8% carbon containing steel, and that is austenite. Now what happens is austenite is cooled. Now see, if we take this line, the first line, then we will see that longer time is taken. As we go to the right, longer time is taken in comparison to this line. So longer time is taken for cooling. Now what does longer time mean? That means what? Slow cooling rate is there. Now during the slow cooling rate of austenite, perlite formation takes place. So perlite forms. If we increase the cooling rate to some extent, so lesser time is taken, and then we will get bainite formation. So here where formation takes place, here the transformation starts and here the transformation ends with perlite. Here the transformation starts, here the transformation ends, and we get bainite. If we increase the cooling rate, this is done by generally quenching. So you can say that if we do oil quenching, so what happens? The start of transformation takes place, but the end line is not intersected by this line. So what happens? Transformation starts, but due to but as it does not crosses this red line, which is the end of transformation, so that complete transformation does not takes place. So what happens is that some of the austenite transform into ferrite and carbide, while the rest of the austenite transforms directly into martensite. Now if we increase the cooling rate much more higher, then what we will get? That means this can be done by water quenching. So what happens is, if the cooling rate is increased, the line will miss even the starting point, nose. It will come towards the left of the nose. So what happens is the whole austenite completely transform into martensite. Now see, from the previous diagram that we have watched, you can see here, at higher temperature the growth rate is maximum, but at lower temperature the nucleation rate is maximum. So with that respect, with that reference, I can say that this transformation takes place at higher temperature. So what happens? Nucleation is there, but rate of nucleation is very less. So lesser number of nuclei are formed, but the growth rate is high. So those small number of nuclei, they will grow rapidly and form larger grains. So this type of grain structure are called coarse grains. Now if we when we decrease the we increase the rate of cooling rate, so what happens is that the transformation generally takes place at a lesser temperature. In this case the number of rate of nuclei formation increases, rate of nucleation increases, so larger number of nuclei can be found, and all of them increase in their size to form grains like this, which are called fine grains. Now if we consider about martensite, there are much more finer grains and large number of nuclei are formed. Another thing, martensite is very much hard. It's too hard, but on the same hand it is too much brittle. So far now we have studied about phase transformation and how phase transformation takes place, and we have learned about the TTT diagram. The next topic of our discussion will be heat tempering, which is very important if we consider the application part. So everyone stay at home and stay safe. I will be back with another lecture.